deliver our research, my team works across a broad front. So we're split into 3 themes looking at different aspects of what do next generation sensors look like. So firstly, we have a theme on hardware platforms, on making custom electronic devices. And there we principally look at flexible electronics. So in front of me, I have our timeline of electronics development. And essentially, each decade, we've had a miniaturization of our electronics, a step change has been there. So in the 1980s, we have desktop computers that start to become widely available, widely accessible. Before that, we had mainframes, we took up a room size. So there's a real miniaturization to get it into this sort of form factor. Then, in the 1990s, more or less, we see laptops starting to emerge. So again, a step change in the portability, in the performance of our electronics. In the 2000s, it's the emergence of the smartphone, which again, a step change down from the size of a typical laptop. And more recently, in the 2010s, we start to talk about wearables, about smart watches and similar, which again, miniaturize our electronics further. The next step in this evolution, and the one which we're researching, is looking at flexible electronics integrated into everyday devices. So for example, we have a cotton t-shirt, meaning that we can make the t-shirt itself the substrate for our electronic. Here we have a tattoo type substrate, which is very flexible. So that work boils down to manufacturing and electronics, how do we make low power devices. Our second theme looks at how do we go beyond just monitoring. To a first approximation, we know how to collect data from a person. There might be limitations in terms of the battery life, in terms of how usable the system is, or in terms of how accurate the data is. But we know how to set up a wireless transmitter to get data from you into the cloud. The next step, and what we're looking into, is how do we get data from the cloud, get it analysed, and then use that to affect or to interact with the person. We're interested in closing the loop with regards to non-invasive brain stimulation. So my team has done a lot of work looking at how do we monitor brain signals. Now we want to use that information to determine how do we stimulate the brain in order to have an effect. So we look at using visual stimulation, or sound stimulation, or tactile or electrical stimulation, and adjusting the properties of that stimulation, say the frequency or the phase of it, so it's tailored to each individual person. And so it's not one size fits all, the stimulation is on or off, it's different people get different settings, potentially at different points of time. What it means is that we have to make low latency, real time signal processing. So typically, we want to get a bit of data, we want to analyse that data, decide what we're going to do, and then take whatever that action is within a few milliseconds, maybe 10, certainly less than 50 milliseconds. And that means we don't have time to run very complex algorithms or to transmit the data sometimes, so round trip time is just too long. And so we focus on the engineering of making that signal processing and making that signal processing accurate, but also very, very timely for use in closed-loop systems. Our third theme looks at how do we integrate wearable devices and other sensors into the healthcare system. The long-term goal for this is to move towards more data-driven digital healthcare. So today, say you have a long-term condition, schizophrenia as a serious mental illness, or chronic kidney disease as a physical health condition. We make no systematic use of all of the data that we can now collect We've got wearable devices monitoring people for very long periods of time, but it doesn't make any difference to the day-to-day treatment that people receive. So we visualize it like this. So we have long-term trends in our different conditions. Regardless of those, people's appointments might be scheduled on a fixed timetable. What we want to move to is something much more like this, where if we don't need appointments in this stationary period here, we can delay them, we can save resources. But when we detect using out-of-the-lab sensors that we're in this critical zone, that's when we schedule lots and lots of appointments and hopefully optimise the care that somebody can receive when they need it. Now this is a really difficult thing to do because you need not just the wearable device, which we're now starting to get available, you need risk modelling based upon the data that's produced from the device. So machine learning, which is looking at patterns of activity and how they might change over time and what that change might mean or indicate. We need to do that not just for the wearable data, but also for the electronic health record data to make sense of where is somebody in terms of the care pathway or in terms of the status of their disease. And it's also got a very complex economic case associated with it and an assurance case, proving that if we delay an appointment here, that actually we're not going to miss that critical event and the person is still going to be safe. We, in my lab, are focusing on the wearable part of this. How do we get the wearable data into this system, look at doing adaptive sampling based upon machine learning to feed such a system. And we're part of a wider project team for delivering some of the other aspects. I think the key, and our key unique factor in my lab, is the way we connect these three different themes together. It's not about doing any one aspect of just hardware, electronics, or devices in isolation, or just software programming, algorithm for devices. It's about connecting those three things together. And when we connect them together in the way which we're discussing here, we end up in a very different place, a very exciting place, with devices which look very different to how they do today.